Ladies and gentlemen, good day. My name is Sganzerla. I am PhD student at University of Campinas, Brazil. In this workshop, I will present the study entitled Subcritical Water Pretreatment Enhanced the Methane-rich Biogas Production from Anaerobic Digestion of Brewer Spent Grains. Starting with an introduction and background about the subject, the food industry in Brazil is a robust industrial sector, responsible to the generation of around 10% of the gross domestic product in 2019, mainly due to the exportation of orange juice, coffee, dairy products, and beer. To produce these products, the industry demands a high amount of energy, which is obtained from non-renewable sources. As byproducts, the industry generates organic and lignocellulosic wastes, which currently are not treated and then are responsible to environmental impacts. Therefore, due to the environment concerns, it's necessary to decrease the carbon footprint of the industrial sector through the correct management of these byproducts generated. The management of organic and lignocellulosic wastes can be an alternative to a sustainable development of the food industry, since with the adoption of an appropriate treatment system, it's possible to recover bioenergy and bioproducts. Regardless of this process, the food can avoid the improper disposal of solid residues and then reach the Sustainable Development Goals established by the United Nations. Regarding the residue generation by the beer industry in Brazil, this sector produces brewer spent grains as the main solid byproduct. An estimate is that 20 kilograms of brewer spent grain is generated per 100 liters of beer produced. In Brazil, we estimate that 7,500 tons of wet brewer spent grain is generated per day. This feedstock is characterized as a lignocellulosic feedstock, and then it's necessary to study and optimize the hydrolysis process for an industrial application to produce biofuels. The literature reports that conventional pretreatments present high operational costs, generate toxic residues, and then the industrial process are non-profitable and environmentally acceptable for industrial application. Otherwise, due to the subcritical water can be an alternative and eco-friendly alternative since use just water as solvent and do not generate residues in the process. In the subcritical pretreatment, the water is close to the critical point and then its characteristics change. For instance, the viscosity and dielectric constant decrease and the solubility and ionic product increase, which make the solvent with good characteristics for the hydrolysis of biomass. Therefore, this study aimed to integrate the subcritical water pretreatment and anaerobic digestion of brewer spent grains to recover bioproducts and bioenergy. For this, the two technologies were studied and optimized in a laboratory study for a further techno-economic environmental assessment. Our goal with this study is to design an anaerobic biorefinery through the circular economy transition of the beer industry. The subcritical water hydrolysis of brewer spent grain was conducted in a semi-continuous flow-flow hydrolysis reactors previously designed and optimized for this feedstock. The process was composed by two sequential reactors of 110 ml, the temperature of 150 degrees Celsius, water flow rate of 10 ml per minute, constant pressure, and kinetics were conducted for 45 minutes. The hydrolysate was collected for analysis and application in the anaerobic digestion. For the anaerobic digestion, two reactors were started up. The first one was coded as AD control and was operated with 45% of wet brewer spent grain and 50% of liquid phase, composed by inoculum and water. This reactor is a dry type since it contains more than 20% of volatile solids in the initial composition. The second reactor was composed by 70% of hydrolysate obtained with the subcritical technology and 30% of mesophilic inoculum. Both processes were operated at a mesophilic temperature, methanogenic pH, and hydraulic retention time of 25 days. Beyond, the process performance was monitored for 50 days in continuous mode, and the biomethane potential was recorded. The results demonstrate that the subcritical water technology was able to hydrolyze the beerspent grain and produce a hydrolysate rich in sugars and soluble proteins. In the first 30 minutes of the process, most of the macromolecules were released from the biomass, meaning that the reactor can operate with a fast residence time, which is a characteristic of this process. The hydrolysis of beerspent grain resulted in the production of arabinose and xylose as the majoritarian sugars, followed by glucose and cellulose. Also, citric and acetic acids were formed in lower proportions. The results of the anaerobic digestion process can be observed. In general, it's possible to note that the pH values were similar for both reactors, with a slightly lower value on the first day of digestion for the pretreated reactor, while the most constrained values occurred for total solids, alkalinity, and ammonium nitrogen. Otherwise, for the pretreated reactor, the total volatile solids and chemical oxygen demand present an increase of 75% and 69%, respectively, which is a consequence of the solid feed implemented in the reactor, since the total volatile solids and chemical oxygen demand of the feed were greater than the values obtained for the digestate. The anaerobic digestion reactor presented a removal of the 55% of volatile solids and 21% of chemical oxygen demand, which is a positive value for the biomass degradation into biomethane. The reactors operated with beerspent grain present a stable methane profile after 35 days, reaching an average of 72% of methane. With the adoption of subcritical pretreatment, the stabilization occurred at day 29 and reached an average of 82% of methane until the last day of operation. Therefore, the reactors operated with hydrolysate obtained throughout subcritical technology produced 35 ml of methane per gram of beerspent grain added in the reactor, against 17 ml of methane per gram of beerspent grain for the reactor operated in dry dredging. The biogas produced can be submitted to a heat and power unit to generate heat and electricity. This electricity potential for the process with pretreatment was higher and reached approximately 35 kWh per ton of beerspent grain, and the heat was approximately 208 MJ. The adoption of anaerobic digestion and bioenergy recovery can avoid greenhouse gas emissions by the replacement of grid energy and natural gas in boilers. In the case of this study, the process can mitigate around 50 kg of carbon dioxide per ton of beerspent grain submitted to anaerobic digestion, which can be considered as a green process that mitigates greenhouse gases. Based on the results obtained, we can propose innovative technological routes to the implementation of an anaerobic biorefinery in the beer industry. Otherwise, regarding the implementation of anaerobic digestion technology, previous study demonstrated that the anaerobic digestion of beerspent grain is profitable and could be suitable for an oncoming implementation in breweries. Also, the integration between waste treatment and bioenergy production could be a solution to reconcile energy recovery, waste to energy, and environmental conservation within the Sustainable Development Goals. Moreover, due to the environment concerns and social policies to reduce the environmental impacts of industrial activities, the replacement of fossil raw materials by more sustainable options is receiving special attention in recent years, and the focus is on the use of residual biomass from agro-industrial processes. In conclusion, the subcritical water hydrolysis can be seen as a promising alternative to to the pretreatment of lignocellulosic biomass for biofuels production. In this study, the subcritical pretreatment increased the recovery of methane-rich biogas and bioenergy, which avoids the burst grain final disposal in landfills, incinerator, or used as animal feed, and a novel destination can be highlighted. Finally, the energy recovery from waste can be a strategy to decrease the brewer's carbon footprint towards a sustainable transition to a circular economy. Thank you very much for your attention.